Hello. I've been working slowly through your homework papers, and I found some problems of interest from this assignment that I think I should go over, just to make sure that the concepts are solid in your minds. Okay, so from this section 32223, I'm finally getting used to his numbering scheme. Like chapter 3, section 2, subsection 2, and then problem 23. Okay, so we find the range space and rank for each map. This was one of the problems I assigned. This function h from 2 by 2 matrices to the real numbers goes from this 2 by 2 matrix to this result. Now, in the answer key, it says the range space R of h equals this. This is not a good answer. Right? It really is not telling you what the range space is. This is the answer here. The answer is that the range space is R. Typically, you should express a range space as a span or linear combination of vectors. Okay. So let me just make that point. So it's best to express, well, any subspace. We can say parametrically. I.e. as the span of a set of vectors. Okay. So, for instance, the better answer is that the range space is equal to. I just learned how to do this. So R of h is equal to the set. You can just call it A, where A is in R. Okay. So, where I could write that A times 1, right? Because 1 is a vector in R. Okay. So, try to express your subspaces or range spaces or null spaces in terms of linear combination of vectors. Notice that null space and nullity are not the same thing. Nullity is the dimension, null space is the space. Okay, so those are two different things. Let me go on to 232 from the same section. Recall that the null space is a subset of the domain and the range space is a subset of the codomain. Are they necessarily distinct? Is there a homomorphism that has a non-trivial intersection of its null space and its range space? So when it's talking about necessarily and is there, that means you should look for examples. Look for examples, okay. So are they necessarily distinct? Okay. Now, so remember what null space is. Null space maps to 0. Whoops, maps to 0. And the range space is the set of outcomes of the function. The set of outcomes, well, I can just say it that way. Or the set of images. So in order to find some examples, then you must necessarily look for cases where the domain and the codomain are the same, because how can you find, of course they're going to be distinct if the domain and the codomain are different, okay? And of course they're not going to have an intersection if the domain and the codomain are different. So look for examples where the domain, in the case where domain is equal to codomain. Okay. All right, now I think it's helpful to think about this in general. A homomorphism can be expressed by what it does with reference to a pair of bases. So you can just think about that. Once you have a pair of bases, one basis in the codomain and one basis in the domain, then you fully specified, and then you can fully specify the homomorphism by what it does on those bases. Now, in this case, I'm going to take the domain basis and the codomain basis to be the same. So let's look at the case where the domain and codomain have the same basis. Now I'm doing this a little more general than you'd have to, just to show you how this could work in any dimension. So let's just take my vectors to be v1 up to vn. And again, I'm not putting the arrows just so that I can make this quickly. So let's specify. All right. Now, if you want to specify the null space, let's suppose v1. So let's specify h on this basis. Okay. Now so the null space is the set of vectors that maps to 0. So let me suppose that I've chosen my null space so that h of suppose that h of h of v1 equals h of v2 equals equals h of v, let's just say vm. So m is some number less than n. And let's suppose all those map to the 0. So when I say 0 here, I mean the 0 vector. Okay. It's not the number 0, it's the 0 vector, right? Because here we're talking about a homomorphism mapping between vector spaces. Okay. And then let's suppose also that v, let's say v of m plus 1, whoops, sorry, I have to do this way, v of m plus 1 equals, let's say v of m plus 1, I'm sorry, h of v of m plus 1. Let's map v of m plus 1 to v1. Let's see, v1. And let's map h of v of m plus 2. Okay. And I can map that to v2. And then dot, 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 dot. Let's, so here, then I would map h of 2m. H of v of 2m is equal to v of m, d sub m. Okay. Now here, let's suppose, let's just to make this easy then let's make this n be 2m. Okay. All right. So what do I have here? I have fully specified. So I have specified the action of h on an entire basis. So that means I've fully specified h, because I can apply h to any linear combination of that basis. Okay. Now I've chosen the images, I've chosen the non-zero images so that they are exactly the vectors that map to 0. Okay. So it's really quite general, and you can construct many examples of cases where the null space is equal to the range space, or the null space intersects the range space. So in this case, every vector in the null space is also in the range space, and vice versa. So it's easy in this way. It's easy to construct examples morphisms with all types of intersections. I mean, between null space and range space. Okay. So just think about what you're doing with a homomorphism is you're basically mapping a basis to a basis. And as long as you choose your basis vectors how you want, the basis vectors in the range space can be the same basis vectors as the basis vectors in the null space. It's really not a problem. Okay, so that's more general. Now, in the answer, you can look at the answer key because it's a very simple example, a two-dimensional example. So if you answer problems like this, it is better to look for very simple examples. All right, so now we have this one. Now I'm going to, in the answer key, he refers to lemma something something, but I want to get some intuitive feel for this problem. Okay, a square matrix is diagonal if it is all zeros except possibly for the entries on the upper left to lower right diagonal. It's 1, 1, 2, 2 entry, etc. So let's just draw a picture of that. So that means, so let A be a square matrix. So I'm going to start this. So let A be the square matrix. Okay, so what that means is that I can write A this way. It's going to have, I can say A1, A2, A, N, 0 here. Okay, where all the, so in this case, so in this is in general. Okay, so A is diagonal. If it has this form. Okay. So that's typically how you represent the diagonal matrix. Okay. So it says show that that the linear map is an isomorphism if there are bases such that with respect to those bases, the map is represented by a diagonal matrix with no zeros on the diagonal. Okay. So let H be a linear map. Okay, and let's suppose that H is represented by a diagonal matrix with respect to bases. So suppose with respect to bases V1, let's say through Vn. And so here, let me just be a little bit more explicit here. Let's say let H. So we'll set let H, and we'll map from V to W. Suppose with respect to V1 through Vn and W1 through Wn, we have the representation from V to W. Let's call this, they typically calls this B. And he typically calls this D. You could use other letters, but that's fine. So it's not rep B, it's not going to be rep BW, it's going to be rep BD. So suppose the representation with respect to bases B and V of the map H is equal to A. Okay, where AJ is unequal to 0. Okay. So what does that mean? So therefore, H of, I can write this way, C1V1 plus ... CNVN is equal to, by the homomorphism rule, it's C1 times H of V1 plus C1 times H of Vn. But these are just W's, right? H of V1. So H of V1 is what? Well, what this A1 means is that V1 maps to A1 W1. Okay, so V1 maps to A1 W1. Why is that? Because if you represent V1 in with respect to this basis, well, V1 is the first basis element. So the representation is just 1, 0, 0, 0, 0. So if I multiply 1, 0, 0, 0 by this matrix, I get A1, 0, 0, 0, 0. Okay? So that means that V1 maps to A1 and V2 maps to A2, A2, W2, A2, W2, etc. Okay? So that means that H of C1, V1 plus CNVN is equal to C1 A1 W1 plus CN AN WN. Okay. Now, here, let me move this down because I'm going to run out of space. Where's my mouse? Okay, good. Okay. Almost done though. Not too much more space is necessary. Right, so let's see. Okay. All right. So how about the inverse? So H has an inverse. What's the inverse? H inverse of so let me just say, the way he typically does it, has an inverse G from W to V given by G of, let's take some linear combination of W's. I guess I'll use D1, I suppose, D1 W1 plus dN Wn. Now, what do I have to do? Well, when I applied H, I multiplied each coefficient by A. When I apply the inverse, I'm going to have to divide. So this is going to be D1 over A1, V1 plus dN over AN, Vn. Okay. Now this is possible since AJ is unequal to 0. Okay. All right. So you can check that G and H are inverses of each other. It should be pretty clear. Now, the way to check that G and H are inverses are each other, you can say G compose H of Vj for any j is equal to Vj, and H compose G of Wj equals Wj for any j. Okay. And that's sufficient to show that these are inverses of each other. Now, if you look in the answer key, he says you can just cite some lemma, but I think that this really shows you what's going on. Okay, if it's diagonal, you're just mapping one basis to another basis with possible scale factors. So to invert the matrix, you just invert the scale factor. Okay, let me make this a little bigger so it's more legible. All right, so consider two linear functions. H from R3 to P2, polynomials of degree 2, and G from P2 to M22, 2 by 2 given here. Okay, so we have two maps. This maps a vector, a typical R3 vector, into a polynomial, and this maps a polynomial into a matrix. We have bases. This basis B is for the space R3. This basis C is for the polynomials, and this basis D is for the matrices. Notice that, of course, R3 is three-dimensional, P2 is three-dimensional, 2 by 2 is four-dimensional. So you know right away that this mapping here is not a homomorphism because it's not onto, right? So there's no way to invert it, but that's not really part of the problem. Okay, right? So it says A give the formula for the composition map G composed H derived directly from the above definition. Okay, well, we can see that. If I want to look, I can see that if I take, again, I can take the a basis, take the standard basis, and find out what this map does to the standard basis. So 1, 0, 0 is going to go to what? It's going to go to x squared plus 2x, which is going to go to, what does that go to? Now that means that, this means that P is 1, and Q is 2, so I have 1, 2, and then this is minus 3. I think I did that right. Let's see. P, Q, I. Well, if I did it wrong, then you can go back and check. So you can also do 0, 1, 0, and that maps to what? So you just go through and take that. Oh, wait a minute, sorry. Well, hang on a second. Let me think about this. All right, well, this is fine. So let's continue. 0, 1, 0. What does 0, 1, 0 go to? I think I may have to zoom in a little bit so I can fit the whole page. Let's do that. Okay. And so what does 0, 1, 0 go to? It goes to, let's see, well, so it's going to go to x squared here. It looks like it goes to the same thing, plus 2x. So it goes to x squared plus 2x goes to the same thing. Okay. And then we have 0, 0, 1. What does that go to? Well, that's my C. All right, so you can see that there's going to be a null space because you're having two things mapped to the same thing. Oops, sorry. Okay, so what does C map to? C maps to C. C maps to C. And C here maps to 0. Okay, so that means that 0, 1, 0 maps to 1, which maps to 0. Okay. So if I wanted to get the general form, ABC maps to, it's A times the first plus B times the second plus C times the third. So that's going to be A plus B minus 3A minus 3B and 2A plus 2B and then 0. Okay. All right, so that's the answer to A. Let's look at B. So it says represent H and G with respect to the appropriate bases. All right, so I'm probably going to have to copy this again. Let's see. Let me take this and copy it again. And here, let's see. I'm going to have to make myself a lot more space. Okay. Right, so now I'm on part B, represent H and G with respect to the appropriate bases. Okay, so how would I do that? Well, let's see. So H, so remember H goes from R3 to P2. Now in this case, I want to see what H does to the basis vectors. Okay, sorry, I've zoomed in. So what does H do to the basis vectors? Okay, so what does H do to the first one? So H of 1, 1, 1 is equal to, let's see, so that's going to give me A, B, and C are all 1, so that's 2x squared plus, and then A is 1, B is 1, so that's 4x plus 1. Let's see, we also have H of second basis is 0, 1, 1. And that's equal to, that's A is 0, B is 1, C is 1. So that's equal to x squared. A is 0, B is 1, C is 1, so that's plus 2x plus 1. And then H of 0, 0, 1 is equal to 1. Okay, now let's represent these in terms of the image basis. Let's see. 2x squared plus 4x plus 1. Now you can see that this is equal to, let's call this one, I guess I'll call this one, no, I'll call this one, what do I want to call it? W1, W2, W3. Okay. So 2x squared is obviously 2 times W3. Okay. All right. So that takes care of this. And then I have 4x plus 1. 4x plus 1, I have to get as a combination of this. So let's see. How am I going to do that? So that means that this coefficient minus this coefficient is 4. So let's see. So I'm going to say, all right. So let me just take a moment to figure it out offline. Okay, hopefully I did this right. To get the coefficients, you have to solve this algebraic expression, because these are the two basis elements, 1 plus x and 1 minus x. And this linear combination must be equal to the 4x plus 1. And you solve it, you get a equal 5 halves, b equals minus 3 halves. So this becomes 5 halves times w1 minus 3 halves w2. Okay. All right, then I have this one. I have to figure out what this one goes to. 0, 1, 1, x squared plus 2x plus 1. Again, this is going to be w3. And then I'm going to have to figure this out again, 2x plus 1. I'll just figure it out the same way. A times 1 plus x plus b times 1 minus x is equal to 2x plus 1. And then that tells me that a minus b is equal to 2. A plus b equals 1. If I add these two equations together, I'm going to get 2a equals 3, so that a equals 3 halves. If I subtract the 2, I'm going to get, let's see, 2b, I'm going to get 2b equals minus 1, so b equals minus 1 half. Okay, and you can check that. Let's see. Just make sure. So we have 3 halves minus 1 half is 1, and then 3 halves plus 1 half is 2. So that would be over plus 3 halves times W1 minus 1 half times W2. And h of 0, 0, 1 is 1. So obviously this one is going to be W1 plus W2 divided by 2. Okay. So what is the matrix? So the matrix tells me that the first mapping goes to, well, this would be 5 halves minus 3 halves 2. So in the vector representation, or according to these bases, okay, let's just write it again. I have h of v1 is equal to 5 halves w1 plus minus 3 halves w2 plus 2w3. And I can think of that as the vector 5 halves minus 3 halves and 2. Okay. Then I have h of v2 h of v2, well, that gave me minus or 3 halves w1 minus 1 half w2 plus w3, and that goes to 3 halves minus 1 half 1. Okay, and then the last one would be h of v3, and that's equal to, what was it? It looked like it was 3 halves W1 minus 1 half W2. Is that right? Looks like, let me think a second. I think I may have made another mistake. Hang on just a moment. I was looking at the wrong place. The last vector goes to 1 half, 1 half. Okay. So this was not correct. This is W1 over 2 plus W2 over 2. I was looking at the wrong place. So this is 1 half, 1 half. Let me just erase this whole equation and move it up. Oh. It's not erasing. Oh well. All right, so h of v3 is equal to 1 half W1 plus 1 half W2, which goes to 1 half, 0. All right, so the matrix representation is simply the matrix with these columns. These give the columns of the matrix representation. Okay, so that means that rep H with respect to these bases, and I even forget what he calls the bases. I think he calls them B and C. B and C, from B to C. And that's going to be equal to just the columns here. First column was 5 halves minus 3 halves. 2. Second column, 3 halves minus 1 half. 1. Third column, 1 half, 1 half, 0. Now I'm doing this very quickly, and I didn't look at the answer beforehand, so if it's wrong, it just means that I made some calculation mistake. The method is correct. So similarly, you can find G. Okay. So let's move this down. The representation with respect to C and D of G. And similarly, you can find the representation with respect to B and D of G composed H. Same way, because you know what the G composed H does to any vector. Okay. So all you have to do is take those So that's how you can finish B and do C, and then just check that the matrices multiply out together. Just the matrix that I found here for H, multiply on the left by the matrix that you find for G, and check that the product is equal to the representation for G composed H. So you can check by matrix multiplication that the representation from B to C of H times, on the left, representation from C to D of G is equal to the representation from B to D of G composed H. Okay. So I'll leave that to you. All right, let me do this one now. Show that if t is square and t to the fourth is the zero matrix, then 1 minus t inverse equals 1 plus t to the fourth plus t cubed. Now this is a very interesting problem because you know if you take the geometric series, if you take the geometric series for 1 minus t inverse, you get 1 over 1 minus x is equal to 1 plus x squared plus dot, 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 plus. So this is actually a special case of this geometric series where t replaces x. So this is like the geometric series where t replaces x. And for this one, you just multiply it out. You just need to check that 1 minus t times this guy here, 1 plus t plus dot 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 plus t cubed, and is equal to 1 plus dot 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 plus t cubed times 1 minus t. I should have said I minus t. It's not really 1, it's I, but the I functions as an identity is equal to the identity. And when you do it the multiplication, there's a lot of matrix cancellation. Most of the terms cancel. And you can kind of see that. Multiply I by all of these, and then multiply t by all of them. And the intermediate terms are all the same. The only thing that's different is the I at the beginning and the t to the fourth at the end. But t to the fourth is 0. Okay. So you can do that. So the matrix multiplication there is really not that difficult. There's lots of cancellation. Okay. Okay. All right, so let's just quickly say something about this. Prove that the composition of the projections pi y, pi x, and pi y is the zero map that despite that neither is the zero map. Okay. So also you can think of these geometrically. What does pi y does? Pi y is, it selects the y component. So that means that the range space of pi y is equal to the y-axis. So that's equal to, I can write it this way, t times 0, 0. Okay. Where t is a real number. Okay. And pi x selects the x component. Now, what's the x component of any point on the y-axis? Well, 0. Okay. So pi x of any point on the y-axis is equal to 0. Okay. So that means that pi x composed pi y equals 0. Okay. And again, here 0 doesn't mean the number 0. It means the 0 map. Okay. And b is going to be very similar. You take the fifth derivative of a fourth degree polynomial, and you've taken more derivatives than there are degrees. So it's just going to go. Okay. And then you can give the matrix representation. Here he says, prove that no zero divisor. So when two things multiply together to give 0, despite that neither is 0, he just said to be a zero divisor. Prove that no zero divisor is invertible. I don't know if anybody actually did this. I haven't seen it yet. So no zero divisor. This is kind of an interesting problem. Okay, so let me just So let me just give you an indication how to think about this. So let AB equal 0, and A and B are unequal to 0. Okay. So we want to show that both A and B have non-trivial null spaces. And that means that they're not invertible. Okay. All right, so let's take them one at a time. Okay. Now, since first, since B is not 0, there exists a V such that BV is not 0. Okay. Otherwise, if you can only get if B maps to 0 for everything, then B is the 0 map. Okay. Okay. Now so BV. So then we also have A times BV is equal to 0, but BV is not 0. So that means that A has a non-trivial null space. Or I can just say so that means that BV is in the null space of A. Okay, so A has a non-trivial null space. So A is non-invertible. Okay, so now we need to show that B has a non-trivial null space. And this one's a little more tricky. So let me prove this one by contradiction. Okay. Okay. Now, what is contradiction? Contradiction means you assume what you want to show is false and show that leads to a false conclusion. So assume that A is invertible. Now we also have to assume the condition where AB is equal to 0. So I could just say A is invertible and AB equals 0. Okay. Now, what does it mean that A is invertible? Okay. So A is invertible. So let's see. Let's consider that means that the matrix representation is also invertible. Any matrix representation of A is invertible. Okay. Okay. Now, for a matrix to be invertible, the matrix must be square. Representation must be square. Okay. Okay. So let's take A inverse. So A inverse exists because the matrix is invertible. Okay. All right. So let's think about this for a second. So let's do it this way. So A inverse exists and is also invertible. Okay. So that means that for any vector V, all right, so for instance, so if we take the BV that we got from part 1, right, in part 1 we said, so take BV in part 1, from part 1, there exists a non-zero vector and we'll just call it W, such that A inverse times W is equal to BV. Okay. And that means, if I take A on both sides, that means W is equal to A of BV. Okay. And what does that mean? W is non-zero. Okay, so AB is not the zero map. Okay, but this contradicts our presumption that AB is the zero map. Okay, so that completes the proof by contradiction. So it's not possible. So the assumption that A is invertible cannot be true. And then given that AB equals 0. Okay. Now there may be an easier way to do that, and if I think for a while I might think of it, but that's one way to approach this. All right, so that's a bunch of problems, maybe get you in shape and thinking about the exam. And I will post these on the Google Drive and hope it's helpful.